to a given state in the bosonic case? No. And there's a strong tendency for them to want to get into the same state. Okay, and we'll try to get to that. All right, this business is a tale of two minus signs. Two distinct, different minus signs. One having to do with spin, and one having to do with what I'll call exchange. But before we talk a little more about the relationship between the half spin and the exclusion principle, let's talk about the Pauli exclusion principle itself, which has a deeper meaning than just saying you can't put two particles into the same state. It's a statement about the nature of wave functions of multi-particle systems. If I have a multi-particle system, and now when I say wave functions, let's for the moment forget the spin, and I'll come back to the spin and tell you what to do about it, but let's forget about spin for a moment and say that the coordinates of the particles that we're talking about are called x sub I. I does not stand for x, y, and z. It stands for particle 1, particle 2, particle 3, and so forth. So x1 represents particle 1, and so forth. And x could be x, y, or z. We're going to suppress the three components of position, just call them x, but I represents the particle. And then a basis of state vectors is to give the positions of all of the particles. Let's write x1, x2, x3. Just as for one particle, we can label a complete set of states by just prescribing the position of the particle. For a system of particles, we can just label all of the positions, and those are an orthonormal family of states, a complete set of states. And just as for one particle, we can define the wave function to be the inner product, whatever the state vector happens to be. This is an abstract state. It's an abstract state of the system of n particles, some number of particles. And the wave function itself is the inner product of the state vector with the specific state vectors, let's call it xn. That is called psi of x1 through xn. What do you do with it? You square it. Well, you don't square it. You multiply it by its complex conjugate. And when you multiply it by its complex conjugate, the result is a probability. It's the probability to find the first particle at x1, the second particle at x2, the third particle at x3, and so forth. So this is multi-particle quantum mechanics in a nutshell. Now, let's suppose that what we're talking about is identical particles. In other words, particles of exactly the same species, electrons, or whatever they happen to be. Ignoring spin for the moment, particles which are identical, we have to ask the question, we talked about it last time, we have to ask the question of whether particle 1 at position 1 and particle 2 at position 2, is it the same state or is it a different state than particle 2 at position 1 and particle 1 at position 2? In other words, that's the blue electron at position x1, that's the red electron at position 2. But electrons don't have colors. They're identical, indistinguishable, and so it's an interesting question to ask, should this state be counted as exactly the same as the state with a red electron at x1 and a blue electron at x2? As far as we know from all experiments as well as from all theory, from quantum field theory, relativistic quantum mechanics, the rule is that these are the same state. So, for example, let's just take two particles. That tells us, for example, that the state that I would label x1, x2, blue particle at position x1, red particle at position x2, is exactly the same as red particle at position x2, sorry, blue, which one was number 1? Number 1 is blue. Blue particle at x2, red particle at x1. In other words, there is no difference between a state with two particles are two particles, say it that way. On the other hand, in quantum mechanics, the physics of a state, the physical properties of a state, don't depend on one particular parameter. They don't depend on the overall phase in front of the state vector. In terms of wave functions, the overall phase in front of the wave function never plays into anything that is physically measurable. That's because all probabilities and all expectation values involve psi times psi star. So it's conceivable that really the right relationship is not that x1, x2 is equal to x2, x1, but something a little bit looser than that. x1, x2 is a phase, e to the I phi, some numerical number, which is a pure phase, e to the I phi of some sort. Well, phi is just a fixed number. It's possible that when you interchange two particles, that the wave function should pick up a phase. On the other hand, supposing you do it twice. Supposing you interchange x1 and x2, and you say, when I interchange x1 and x2, the wave function should get multiplied by the phase e to the I phi, and then you do it again. You interchange them again. You get back to the same place. You get back to the same place. You get back to the same state that you started with. In other words, when you interchange twice, you really do have to come back to the same thing. No other possibility. So the general guess would be that e to the I phi here is either plus or minus 1. It's an operation. When you do it twice, you get 1. But there are two possibilities. There are two sensible possibilities. Well, you might say only one sensible possibility, but then you'd be leaving out half the particles in the world. Plus, bosons, particles which satisfy that property, that when you interchange any two of them, and in fact it could be a multi-particle state where you just take any two and interchange them, if the state is exactly the same, then they're called bosons. So bosons satisfy the property that the wave function or the state vector, when you interchange any two of them, stays the same. Fermions are the case with a minus sign. Okay, so when you switch two fermions, identical fermions, the state vector changes sign, keeping in mind that the change of sign is itself not observable. It's not an observable thing because the probability distributions, expectation values, everything of interest involves psi times psi star. All right, so if the state vectors change in this way, then the same must be true of the wave functions. For example, let's take x1, x2 psi. That's by definition psi of x1 and x2. Whoops. Wave function of particle 1 and particle 2. On the other hand, x2, x1. That's equal. the psi of x2, x1. In other words, the two wave functions are related to each other just by switching the arguments. But now, if the state vectors themselves have this property that they either change sign or don't change sign, then the wave functions must have the same property. So this becomes a property of wave functions. And let's write it down. If you have a wave function for fermions, for a system of fermions, x1, and now let's just do it for two particles, and then I'll tell you what to do for many particles. The rule is, for fermions, it must be equal to minus what you would get if you interchange the particles. To interchange the particles, the wave function changes sign for fermions. What about bosons? For bosons, no change of sign. Plus. Okay, let's think about some states and see what sense we can make out of this. Supposing let's take the case of bosons first. The case of bosons is a little simpler. No change of sign. Let's suppose we have two bosons in two different states. Well, one state could be